All right. Hi, and welcome back. So today I'm going to be showing basically just the solution to this problem. This one is a lot more tough than the previous one about convex sets. So here we have let S be the family of subsets of V. So S is the power set of V, if you're familiar with that, where V is of size greater than 0 and of size less than infinity. So V is some finite non-empty set. So we say that S is laminar if for all pairs of subsets X and Y of S, where X and Y are not disjoint, right? So their intersection is not the empty set. We have one of two cases. Either X is a subset of Y or Y is a subset of X. Okay. So we want to show that if S is a laminar family, then the number of elements in S is less than 2 times the number of elements of V. All right. So this is probably pretty new. Anybody who's watching this, it's pretty unlikely that you've seen this laminar concept before. I don't know. It was the first time that I had seen it before when I saw this problem. But let's just get right into it. So let's think about some examples first, right? What is not laminar? Well, basically, if you have, let's just draw out some possible sets, right? Let's say the set, let's say that V is equal to 1, 2, 3, 4, right? If we just draw some circles around those to indicate subsets, then this subset of subsets, that's laminar, right? Because it obeys the property. Now, there happen to be no pairs that are not disjoint, so of course they obey that property. What about now? Let's add another subset. So now we have a pair that's not disjoint, right? So we have this pair between these two subsets, and we have this other pair here. Right, so the one around 2 and the one around 1 and 2, the one around 1 and the one around 1 and 2. Now, because this subset, right, is contained inside of this larger subset, and the same thing goes for this subset and this larger subset, the set of subsets is still laminar. All right, now what about this? What if we take this? And then let's say that we have this other subset here. Well, not anymore, right? So you can see, that we have these crossing lines, which indicates that there's an element in one set that's not in another set, and that these sets both have elements that are not necessarily contained, right? So this set over here containing 2 and 3 is not a subset of the one containing 1 and 2. And the one containing 1 and 2 is not a subset of the one containing 2 and 3. So this would not be laminar. Okay. So now let's step back and let's try and maximize the number of sets that we can have. So we're going to try and push up against this supposed bound of 2 times the number of elements in there. So let's think about how we can do that, right? Now, we know that we can have, really without losing anything, we know that we can just put every individual element into its own subset, right? So let's do that. Let's keep drawing out an example. Let's just keep our old example, V equals 1, 2, 3, 4, right? So we want to say that then the number of possible subsets that are allowed to be in S is going to be less than or equal to 8, right? Because 8 is 4 times 2. So let's just put every element in its own set, all right? And now we have, well, how many, what's S now? The cardinality of S, it's 4, right? Or, yeah, right now it's 4. So let's try and increase that. Now, what's the best way to increase that? Well, if we take a subset of 3 elements, right, then that's going to kind of limit us because we won't really be able to do anything except for taking the larger subset of 4 elements after that. What about we try taking subsets of 2 elements? So let's take this 1 and 2. Now we can't take 2 and 3, right? Because that would as we saw before, not be laminar. So let's take 3 and 4. Okay. And now S is what? S is no longer 4. Now it is, well, we added 2 more, right? So it's 6. You might be able to see where this is going now, but let's keep going. And now what? Now we have, really, we only have one other subset that we can take while keeping V laminar, right? And that is the entirety of V. So this, and we've just added 1, and that's 7. So is 7 less than or equal to 8? Yes, it is, right? So 7 is less than or equal to 8. This is, it seems like it's really the largest possible, we're getting the maximum number of subsets out of this while keeping S laminar. So continuing along that line of thought, obviously this is going to be a proof sketch, not really a full proof. If you want to, do that on your own, that's fine. But just kind of going over the main idea behind this proof. If we keep going, in a more, I guess, algorithmic sense, or maybe a more formal sense, what are we doing here? Well, if we look at this, first we had, this is V. This is the size of V that we had, S, right? Then what did we add? We did the 2 element subsets, right? So it's plus this, and how many 2 element subsets are there? Well, they're going to be around 2. Really, it's going to be the floor of this. Oh, yeah, sorry about that. That is, that's supposed to be a 2, not a 4. Okay. All right, and then what are we adding? Well, we're going to divide by 4 now. And of course, take the floor of that. All right, and now if V was larger, right, you can kind of see where this is going. We'd be able to maybe do 8, right? So all groups of 8. Or, yeah, all groups of 8. And then that would look like this. Okay? And I think you can see where this is going to end up. So first, we know that this is going to be bounded at something, right? And if you're familiar with series at all, you can definitely see where this is going. As the size of V approaches infinity, we're going to approach this thing, right? So we have, now we know this is less, this is actually greater, right? So this here, because we're taking the floor of everything, after when we start dividing, is going to be actually less than what I'm going to write underneath it. So if we just get rid of the floors, size of V over 4, size of V over 8, etc., right, etc., because I think you can see where this is going. We can rewrite this. Let's factor out the size of V. And we're going to multiply this by what? Well, as V goes to infinity, we're going to get this. We're going to get, let's say, n equals 1. No, let's do n equals 0 to infinity, right? Oh, that looks like a shitty 8. It's a little bit better. We're going to get 1 over 2 to the n, right? Okay, and this is accurate, right? We have factoring out this v. If we factor out the v, this gives us 1. This gives us 1/2. This gives us 1/4. This gives us 1/8, right? This similar, right? This is 2 to 0, 2 to the 1, 2 to the second power, 2 to the third power, right? So as we expand this, yes, it lines up, and we factored out this v. And now, what does this series converge to? Well, it's going to be 1 over 1 minus r. We can tell this is a geometric series, right? What's the common ratio here, or the geometric ratio, whatever? What gets multiplied at each step is, it's going to be 1 over half, right? 1 to 1/2, that's 1/2. 1/2 to 1/4, that's 1/2. So this is going to give us 1 over 1 minus 1/2, which is 1 over 1/2, or 2, right? So this is 2. And so this is going to be equal to 2 times the number of elements in V. Right, so there it is, right? We finally found our term that we were looking for. And we know that it's going to be less than this, right? Or less than or equal to this, because we have these floors here, right? So we have, finally, size of S is going to be less than or equal to 2 times the size of V. And this is for all laminar families of sets, laminar, I guess, families of subsets of V, right? And so, again, this is just a proof sketch. Obviously, if you want to prove this, you'll have to go into a bit more, you'll have to use a bit more rigor. But I think the idea comes across pretty well. And that's it for this video. So thanks for watching.